From the campus of the University of Kentucky, this is Behind the Blue. I'm Cody Kaiser with UK Strategic Communications.
So UK has this unique capability that no other university I would even claim in the world has, which is very specific, but it's to be able to do a lot with heat shield. And by a lot, I mean pretty much everything. Be able to test them, measure the performance, and then we have the unique computational tools to be able to take these measurements and then predict what's going to happen in flight. So we have this again, very unique program where students participate as undergrad up to PhD students into building, designing, analyzing space capsules. So these capsules are sent in space, they're sent to the space station, and they essentially re-enter Earth and just testing material. So really the goal here is to cover everything. So we make the material, we characterize the material, we test the material, we make prediction with the computational tools, and then we actually can test them in flight. So again, this is a very unique capability that no other university has.
That's Alexander Martin, a professor of mechanical and aerospace engineering in UK's Stanley and Karen Pigman College of Engineering. When NASA's Artemis II mission sent 4 astronauts around the moon and farther from Earth than any humans have ever traveled, one of the most dangerous parts of the journey came at the end, during re-entry. The spacecraft returns at extreme speed, and a heat shield is what stands between the crew and the intense heat created as the capsule meets Earth's atmosphere. On this episode of Behind the Blue, we're joined by Martin, Savio Puatingle, and Michael Renfro, UK researchers who've helped NASA learn from Artemis I and strengthen the thermal protection systems that make missions like Artemis II possible. You'll hear about why re-entry is so challenging, how UK's research helped explain what NASA saw after Artemis I, and how students are central to this work, from lab analysis to flight testing materials in UK-led capsule projects.
As you introduced yourselves to me, Alex, Savio, and Mike, thanks so much for being with us on Behind the Blue. I'm going to ask each of you to take a moment and actually formally introduce yourself to people who are listening. So tell me who you are and give me a little bit of your background as to what you do here at UK.
Okay, so I'm Alexander Martin. I'm a professor of mechanical and aerospace engineering. I've been in the UK for 16 years now. I came to do heat shield research, which is and hypersonic research. So I've been doing that for the last 16 years now. Yeah, that's about that.
I'm Savio Puatingle. I'm an associate professor in mechanical and aerospace engineering, and I also do a lot of research in heat shields, modeling, testing, and I've been at UK for about 6 years now.
And I'm Mike Renfro. I'm a professor in mechanical and aerospace engineering. I've been at UK since 2015. I came here as the department chair of mechanical engineering initially, and I continue to work about half and half between administrative work and work as a faculty member. My research background is in combustion, laser diagnostics work, and I've got into this heat shield work collaborating with Alex and Savio about 6 years ago.
Excellent. So I want to take a kind of a big picture look at kind of what we're going to be talking about today, and then we'll get into a little bit more granular stuff. But for people who I want to try and be hopeful and say that there's not many people listening who haven't heard about this. But for listeners who have not been following the news about Artemis, can you give people a brief kind of overview of what is Artemis II, and why this is historic?
Well, okay. So the Artemis is the overall big picture project / vision for the US to start having a base on Moon, start commercializing on Moon, eventually going to Mars and settling on Mars as well. So essentially, we want to go back to Moon, but it's going to be different from the Apollo era. We want to settle a base, commercialize it, have manufacturing on Moon, produce things, live there for sustainable periods. So you can't just go from not being there to suddenly, voila, it's there, right? So you have to go through a series of steps. So there's going to be a series of missions, Artemis 1, 2, 3, 4, before we eventually land people on moon and then start living there sustainably. So Artemis 1 was an uncrewed mission, so there were no astronauts on board. It went around the moon and came back. Artemis 2 had astronauts on the vehicle, and again it went around the moon. It did not land; it went around the moon, and it came back. And with 4 astronauts, this happened last month, right? And so then Artemis 3 is going to be. It's still unclear, but I think there's going to be a landing, and then eventually, I think a human's going to land again with the Artemis 4 mission.
And Artemis 2. This particular group of 4 astronauts, this is the furthest distance that humans have traveled from Earth, correct? Because of the
That's right.
Because of the orbit and how far around the moon it actually took us. And so the work that the 3 of you have been contributing to is not necessarily part of the getting there, but it's the critical part of the getting back, which is the heat shield work for when the vessel, the capsule actually returns to Earth and enters the atmosphere. And so when people hear heat shield, I know that it's, they're kind of on a basic understanding of like when you're coming in, you're encountering, a thicker atmosphere the closer you get. That causes friction, heat buildup. But kind of give people an idea of like what they should picture with this and why this is such a critical part of a crewed mission and why it's so critical in the sense of like, I think a lot of people are like, well, why do you have to come in at this speed, or why do you have to come in at this angle, and why do you have these factors? Can't you just kind of gently kind of bring yourself down, use thrust to slow your descent? Like, give me a little bit of background on why this is the way it is and why it's important.
Yeah. Well, okay. So we're coming back from farther away, right? So just to be in orbit, you're potentially at 7 kilometers a second. So that's a lot of speed. So it's all about the speed, right? So whether you're in orbit or you're coming from the moon, you're coming in really, really fast because you're going far away. So you need to go fast to make it a journey that is reasonable. So that amount of energy that you have, so the kinetic energy induced by speed, when you're landing, it needs to be 0, right? Because you're slowing down to 0. So if you were to use a deceleration, so to a power deceleration, you would require a huge amount of energy to slow it down. So the easy way, let's call it, is to use the atmosphere to slow you down when you're coming down. But energy is conserved, right? So whatever kinetic energy you had when you're either coming down from orbit or coming down from the moon, will need to be somehow transformed into something else. And usually it ends up being heat. And that heat, you wanted to prevent that heat from actually reaching your vehicle. So that's why you need a heat shield. So heat shields are very complex. They have multiple physical factor that makes it that you can remove that energy. So they're transforming, for instance, the kinetic energy into chemical energy. And there's a lot of these energy bucket that you can use. But in the end, you're going to have a lot of thermal energy, and you need to protect the vehicle from thermal energy. Just to give you an example of that, if you're looking at a reentry like that, so a few millimeters from the surface of the vehicle, the temperature of the gas is in the tens of thousands of Kelvin. So something that's far, far hotter than the surface of the sun, right? And that's happening a couple of centimeters right in front of the vehicle. So you want to protect your payload, you absolutely need a heat shield.
When I think of this particular capsule vehicle, it's very reminiscent in ways of like the Mercury and Apollo missions. It's dissimilar in ways to what their most recent point of experience generally is as far as like the space shuttle, which had a completely different kind of configuration. This is kind of similar to that in some ways as far as shape. But how have we advanced and progressed? I'm sure materials have changed immensely in the 50, 60 years since then, but How has this how has this changed from a technological perspective, and then also from your approach to how you design such a thing?
Well, one difference between the space shuttle and the missions coming back from the moon or further away is that the heat that has to be dissipated coming back just from orbit can be done with a ceramic material, a reusable ceramic material. So the tiles that people were familiar with on the space shuttle are sufficiently resistive to heat flow that they can be reused, and you can survive, a landing with that material. But coming back even just from the moon, the extra velocity requires a higher heat dissipation, and those reusable materials don't work anymore. And so you need an ablative heat shield material. So this is something that is deteriorated as it's entering the atmosphere, as material is being ejected from it, and that's part of the heat protection process. And so that's really what we've been working on, is that ablative heat shield material.
And so you have a particular amount of time, a certain amount of energy, a certain amount of time that you're going to be losing. So that all goes into the design of this to figure out how thick this needs to be and how much material you can lose over a certain amount of time before you get to a point to where it's not an issue, I guess, at that point.
Yep, exactly. I think that's what it is.
That's good. That's good. I feel
so
like
much energy has to be lost and cooled in a certain amount of time, and the heat shield has to have a structure and thickness that ensures that it happens. If you think about it, in some ways, it's a necessary evil type situation, right? Ideally, you don't want any heat shield because it's just a waste, but you need enough to make sure everybody's safe, humans and the instruments.
And most people, I think that the launch is the most dangerous part, but the coming home is just as intense, if not more so, correct?
Yeah, there's still three technologies that are a concern for NASA. So batteries, parachute, and heat shields. So yes, it's always a concern.
So after Artemis I, after that mission returned to Earth, NASA noticed some unexpected wear on the heat shield. So can you talk a little bit about that, and what did they see? And then maybe talk a little bit about kind of how that triggered a bigger investigation.
So yes, but before that, I just want to mention too, there was a previous mission so Artemis I was a name changed, but before that there was the EFT-1 mission, which predates this, which was extra orbital, didn't go around the moon, but it's part of the same series. So UK has been involved with NASA on these type of heat shields. So the Artemis mission, even before it was called Artemis, for EFT-1.
Okay.
So there have been some change, and I think that leads to your question. So there's been a structural change in how the heat shield was constructed from EFT-1, which worked really well, to what Artemis I heat shield was changed to, and then what led to the change. There's no real change on Artemis II, but led to the need to rethink of the entry based on what was seen on Artemis I.
So what was that underlying issue that I guess NASA needed to understand before we sent people up?
Well, there's the original heat shield for EFT-1 is basically a copy of the Apollo heat shield. So going back to your question, so the way NASA operates, and I'm not criticizing this, I think this is the way to go, is to if something works really well, you keep going with it. So even though there's been, again, to your question, there's been changes in how materials were developed over the last few years. If we're thinking about other missions, like to Mars, for instance, they were not using the same material. But for a mission with humans coming back from the moon at that speed, NASA went from for the type of heat shield that they had developed in the past. But they did make a significant change before when they went to Artemis I by removing some of the structure and making tiles. Instead of having a but a monolithic heat shield, they went to tiles. And that led to some of the issues with the heat shield.
Okay. And so some of my understanding was having to do with some of the pressure that was building up kind of inside of the material?
Yeah, so these ablative materials are a fibrous, porous scaffold that is filled with resinous material, and that resin material is what ablates during the reentry. So the the resin material will pyrolyze, and then gases will form a gas that flows out of the heat shield, and that gas pushes against the incoming hot gases, and that provides a lot of the thermal protection. So these gases that are formed in the heat shield have to get out. And the way they get out is pressure builds up within the system so that the pressure can overcome the pressure pushing back against it and have the gas come out of the system. If the fibrous network is too tight, let's say, if it has too low of a permeability, the gases don't flow easily. You need a much higher pressure to push the gas out, and that high pressure can then lead to structural failure in the heat shield material as well. So the cracking that you can see in this can be caused by excessive pressure that's built up from this gas in the system.
I know we're talking about technology and mechanical type technology, but this in so many ways, maybe I'm wrong, but sounds a little more rooted in biology as far as like a permeable or semi-permeable membrane that I remember learning about in school. I mean, are the mechanics somewhat similar to that?
I mean, yeah, these porous materials are used in all sorts of places, so that you might see them in those applications. But I mean, rocks are another example of porous materials with waters that flows through them, and these exist everywhere.
As far as your work and the work here from UK, how does the university fit into this bigger NASA team effort, and what questions were you kind of brought to kind of help answer? I mean, maybe a little more so than what you've kind of already explained. Like, how did this kind of get the ball rolling here?
Well, so I think when there were issues with the first Artemis I heat shield, right, we were sent flight samples to analyze. And as Mike was mentioning, you can have pressure buildups based on how the pores are, right? And that allows the gases to flow out or not flow out, and that could lead to cracking and so on. So these measurements are interconnected with the structure of the material. And so we have some unique facilities at UK, at the Electron Microscopy Center in the Pigman College of Engineering, that we've leveraged quite a bit, where we can look at material structure at micron level resolution. So 1 micron is in about 1,000th of thickness of your hair, right? So when you can start looking at such small scales and how the structure of this material looks like, you can kind of correlate, this is the structure, and you can easily see why it behaved the way it did, right? And so providing that information to our NASA leads, right, that allows them to understand, okay, we understand why the structure happens, so how do we design these heat shields for the next missions to prevent these type of structures that can lead to pressure buildup, right? And tune the structure in a way that allows them to meet the mission needs.
Oftentimes we hear about mission work that goes on, both that happened with the space shuttle program and also happened and currently happens with the International Space Station, that there are a lot of experiments that are carried out in space or low Earth orbit that you just can't do here. You do some things there that the conditions allow you to do. On the inverse of that, how do you test such a thing here for, like, what are the complications and the things that you have to figure out to be able to say, we're going to test this here versus, you can't really do a test necessarily up there. So how does that kind of factor in?
Well, I think that's essentially the challenge in these type of engineering problems. You cannot test on ground. The only way to test is to fly. And so a related kind of field to space capsules and reentry is hypersonics, and the US is heavily invested in it. And if you read like popular magazines, you'll just see an increased cadence of flight testing. And that's because it's very hard to replicate aspects of flight on ground. And so the true test is to just fly it, right? And so you can do parts of it on ground and try and stitch them together and try and understand what is happening. But you're right, like the true test is just fly them. And we actually at UK have a program where we fly space capsules started by Alex 16 years ago. And we're the only ones that run this flight program. So maybe we can deviate there quickly and talk about that.
Sure, yeah.
Go ahead, Alex.
not to throw you back into the.
Well, I mean, if you're okay with that.
Yeah, no, absolutely.
Okay. We need to go back to Artemis at some point, though. Yes. Yeah. Well, so
it's an open format podcast. So we can kind of meander around as much as we want.
Yeah. Well, so UK has this unique capability that no other university I would even claim in the world has, which is very specific though. But it's to be able to do a lot with heat shield. So, and by a lot I mean pretty much everything, which is not make it.
Not yet.
Well, almost, but also, but be able to test them, characterize them, which is what we did for Artemis. So measure the performance, and then we have unique tools, computational tools, to be able to take these measurements and then predict what's going to happen in flight. And then the third leg of this is to have testing capabilities that we have as well. So be able to generate that amount of energy that the capsules see, and then expose materials to it and to test it and verify their prediction on the ground, right? And then the fourth part of this is that we can also fly these materials. So we have this again very unique program where students participate as undergrad up to PhD students into to building, designing, analyzing space capsules. So these capsules are sent in space. They're sent to the space station, and they essentially re-enter Earth and just testing material. So we're at round 3 of these right now. We did they're called CRAPE, the mission, the CRUPS capsule, the CRAPE flight. CRAPE 1 was 3 capsules. Sorry, CRAPE 2 was 5 capsules, and CRAPE 3, which is going to happen in a couple of months. The capsule are already on the space station right now. There's 12 of them.
Wow.
So really the goal here is to cover everything. So we make the material, we characterize the material, we test the material, we make prediction with the computational tools, and then we actually can test them in flight. So again, this is a very unique capability that no other university have.
Actually, there's some serendipity in you being asked about this and kind of talking about it, because talking about students was kind of the next direction that I wanted to go in. So this is good. I want to talk a little bit about that, in that we've got students who are very much contributing to all of this work. And I wanted to ask kind of what roles that students are playing, and what level are we talking about? Are we talking about, doctoral candidates, masters, or are we talking even at the undergrad level when students come? Are they helping to contribute to this type of research?
Yes, all. Yeah, I mean, we have students at all of those levels. I mean, I think the PhD students carry the lion's share of taking a project from beginning to end, but there's lots of master students and undergraduate students that work with them. And then the CRUPS mission that Alex was talking about was started explicitly as an undergraduate design project initially, and then grew into the big program that it is today.
So how do they contribute to this work? Like, what roles do they play in this?
Well, I will rephrase it as they lead the work in many aspects. They're doing almost all aspects of the work. They are truly the experts. They understand these. They are experts in these equipments, and they're experts in running them, collecting data, analyzing them, and advancing the field. Right? That especially the doctoral, like PhD students, are advancing the field through new capability developments and new tools that can transition to NASA or other agencies. At the undergraduate level, they're learning these techniques, but still like working with our materials that are of interest to us. So they're contributing at all levels. And in fact, my role really is find the project and facilitate the initial discussion, and then step out of the way, and the students just take care of it all. So they're not just contributing, they're leading all of it. And that transitions because now our students end up at NASA or other companies as federal labs. And that creates this nice diffusion of knowledge where they take kind of the leading edge stuff that's happening at UK in our department and transition that into these centers that need it as well.
I was going to say that's got to be a huge, opportunity for them to come here and do this, to be able to add that to their resume as a student, to be able to go out and and once they finish, go out and join the working world with this type of background. And I would imagine that that's a big attraction for a lot of aerospace research, or just, a lot of different types of research, to be able to go out and get a job. So, seems like, this really sets up our College of Engineering in really rarefied space in a sense, or rarefied air.
Yeah.
Not to be too punny.
Yeah, and I think the coolest thing that I've experienced in the last 6 years is we've made an effort to hire our undergraduates from Kentucky into our doctoral program, and that's a very fulfilling experience, because these are students. When I first pitched them like a PhD position, they've not even thought about grad school as a possibility, right? And they just wanted an engineering degree just so they could have some job, and just in many cases come out of poverty. They're first generation kids in Kentucky. So being able to offer this opportunity, and then you see them competing with the best in the nation, right? And then they realize what's possible. So I think being able to provide that opportunity is probably the coolest thing of my career in the last 5-6 years.
I would imagine it has a massive impact upon just their motivation to do this work, when they realize that, you're going to have a chance to work on something that's connected to an actual NASA mission. And we're not talking about theoretical things. This is actually, in development and in use.
Yeah, and it has a lot of synergy with another program that Alex runs in our department, the NASA Kentucky programs. You may want to talk a little bit about how that ties into this, student opportunities.
Yeah, that's another tangent.
All good.
So we have at UK, so it's run through UK, but it's a state program, which we call NASA Kentucky, but it really is the Space Grant and Kentucky EPSCoR programs. So this is a program that is meant to, so it's funded by NASA, and the idea is to provide resources to states to grow their research in space technologies or science. So through that, we fund, there's two axes, but there's a educational aspect of it. So the Space Grant is really to try to get students interested in that, provide funding, so as undergraduate, as graduate students as well, so that they can do research and have education in space. And that is even broader than that, because we also fund a museum and learning center throughout the state. The other aspect of this is more research, and this is where we decide to have some targeted discipline that we already had some expertise in, and try to make it really our own, not to spread our research too thin, at least for the moment. And that's part of that. So we've targeted, one of the target that we did was hypersonic a long time ago, and that was prior. I had this hat. It was Dr. Suzanne Smith, who kind of took that direction and tried to really own in on a very specific aspect and become an expert on it. And I think that's what she managed to do, and where we are now is partly because of that.
I remember talking to Dr. Smith. I've been at UK for about 16 years as well. I came in 2011, and I remember talking with Dr. Smith a few different times in the first few years that I was here about different projects, aerospace type projects she was working on, talking about drones, talking about things like that. So I'm familiar with some of the work that she had worked on back then. So Artemis is a long-term program, kind of steering back to this area. How do these missions, I guess, I know you kind of touched on it briefly, but this kind of is an early step in this roadmap towards sustained lunar exploration, eventually Mars. And how does our learning, in a broad sense for people listening, what we learn kind of roll into the next mission and the next mission to kind of help advance that and make these things, more efficient, easier to pull off in a sense?
I think a lot of it is confidence building, right? So Artemis I had issues. We studied it and we figured out what the issue was. We fixed it. Artemis II was 100% success, right? There were no issues as far as we can tell. So which means we learned, we fixed it, and we iterated and got better, right? But there's still learnings from Artemis II, right? All of these missions have tons of sensors on the heat shields, but also other aspects. For example, they carry bone marrow of several astronauts to see how their bodies would respond in these long duration missions, right? So you learn from that, you iterate and get better, right? So now at the third attempt, there's still, I think NASA is still finalizing, but third one would be a quick landing on the moon, likely, right? And so now that you're confident that you can fly around and come back safely, you can attempt the next step. And so you take one step at a time, learn from it, iterate. And I think a huge part of it is also like modeling. We had briefly mentioned that the best way to test your system is to just fly it. But you can also do a lot of modeling. And that is something that has significantly improved over the last 50 years since the Apollo era. Our computers have gotten better. Our ability to model them on computers have gotten better. But, I always say, whatever you do on a computer, just numbers and pictures, unless you can validate it with the real data, right? So as we get real data and we start validating all these models, it increases the confidence and the reliability of these, right? So it improves our knowledge, and we get more and more confident that this can be done. And so that's how each mission leads to the next and helps us be there.
The gap in time from the Apollo era to now, I've heard people talk before about how like we just kind of shelved so much of the technology and knowledge about this, and to do this again after so much time because of the fact that we just kind of mothballed all of that, it made it such a heavier lift in their opinion. Is that true? I mean, was this way harder? Was there a lot of like, there's so much work ahead of us, despite having all of this previous work that we had done because of the amount of time that had passed? Was it daunting in that sense?
Yeah, it's the little details, right? So a lot of the scientists that work on Apollo ended up retiring, even passing away. So there was loss of knowledge there, even though try to document everything, it's all about the little details. So that was an issue because that technology was essentially unused for 20, 30 years. Yeah.
So it's almost a rediscovery of things. Yep. You have to like rework through a lot of the same problems that had been done before.
And our risk tolerance is a lot less now than it was then.
Sure.
So the depth to which you have to work the problem and make sure that it's not going to fail is at a much greater bar than it was then.
And I would think that the risk tolerance even then was probably pretty rigid, but even more so now. I mean,
well, I think what I've heard, right? I haven't personally verified this. There's this reliability number that people give. So, right, if you say 0.9, right, or 0.99, so every time you add a 9, the amount of effort that it takes to get that extra digit there in reliability. So if you think of 1 as 100% reliable, which you can never be, if 0.9 is easy to get to, 0.99 gets much harder. And then if you add another 9, it's exponentially harder. Somebody gave me this number, a senior person, and I haven't verified this, but I think the Apollo era was 0.99. And that was a number that they just, decided to say, oh yeah, that's good enough. And that required 4% of the GDP in that era.
Right.
And apparently after the missions, when they went back and did the numbers, if they had decided it would be 0.999, the testing would have required around 60% of the country's GDP.
Wow.
So, and now we are at those kind of numbers, right? So to Mike's point, like the rigidness and the requirements have gone up a lot. Another thing I was trying to explain it to my brother-in-law last week, it's a little bit also like remake Star Wars, right? But remake Star Wars with the technology of that era. So before you even start making the movie, you have to go and find real films. You cannot use computers.
Sure. Yeah.
You cannot use CGI.
Yeah.
You go find floppy disks or whatever, right? So if you spend 4 years just finding the equipment to make the things from 1970s or 80s that have since retired, right? So I think that was the biggest challenge for them.
So, looking forward now, we've got a lot of takeaways from this, a lot of information that you're working on. So we've come, back. Where then do you go from here? This is where the work kind of begins in a sense. Now you've got new data data sets to look at. So what do you continue to work on from here that builds on this, and how does the university contribute to the next missions after this?
The short term is that we have several of our students that are going to spend the summer at NASA actually working on Artemis II data, which is pretty exciting. So to be able to have both the work we did for Artemis I and then Artemis II, being able to see what happened, that's going to be great.
Kind of like what Alex said, like it's, we've got a bunch of data from Artemis II, right, that students are going to analyze in the summer. And as we learn more, we can characterize these materials more and keep building the confidence in our ability to predict how they will behave under these extreme conditions.
And we're always like updating, they're updating their models. I'm updating the experiments to try to get the next thing. There's things we can measure now that help to understand what happened with Artemis I, but there's things we can't yet measure. So we're always trying to just chase that next little thing, make the experiment a little better and understand it a little deeper. The
built-in factor is that with whatever answers you get, it creates more questions, correct? And you just
hopefully
go from there. Right.
That's the fun.
So let me just kind of wrapping some things up on a personal level. What is the moment that what is something about this that you're most proud of with this project?
Well, for me, we have flight samples. It's in Mike's room, but I can always knock and be like, can I look at them? So, I mean, we didn't buy it on eBay or anything. People from NASA like coded out for us and sent it to us. So that's like some of those like dreams, and like, collaborating with NASA folks. We know some of the mission leads. For me, it's like, you talk to them, and every now and then when I sit back and I go like, oh my God, I cannot believe I know these people. So that's the coolest thing for me.
Yeah. I think like the proudest moment is we've been working on making this experiment that could do these measurements for years, and really doing more of a scientific study. But Artemis I has a problem, and the first place they want to send it to is Kentucky. That's like UK is where this needs to go to get answers, and that's kind of cool.
Yeah, I think that's the overall thing, is to have been able to have a university that's not necessarily well known for its aerospace research over the last few years now has become a reference for that kind of studies. So taking the state of Kentucky, which again, not very known for aerospace, and now is one of the leader for that kind of research. So that's been great to see that growing.
That is pretty cool. What is one misconception, if you could, you have the platform now, you have the microphone, one misconception that people may have about space research at a university, kind of tying into what you've just been talking about?
Well, there is always, I don't know where to start with this.
I just said just one.
Yeah, I don't know.
Well, maybe, I don't know if it's a misconception, but there might be, maybe I think people think space research is very hard and it's done by like people with a lot of expertise or like geniuses and whatnot. But I don't think at Kentucky, as we've talked, we have kids from freshmen working on these projects, and you learn along the way. So I think the misconception is that it's inaccessible, but that's not true. I think it's very accessible and to all majors, right? Space research is not for aerospace people. It's for all engineering people and science people. And I will also say arts people, because some of the design stuff that maybe more SpaceX focus on, but I still love all the cool like new spacesuit designs and stuff. So it's for all.
Yeah, I think that it's good to have people see that you don't have to be from the like most base level. You don't have to be at a university that is like in the desert or in Texas or in Florida to be able to work, or California to be able to do these things. You can do it right here in Kentucky, central Kentucky, and the foothills of the Appalachians.
That's right.
To do this same type of work.
You don't have to be at MIT to work on Artemis.
Right.
And you can be from Appalachia and work on Artemis and be very significant.
In talking about UK and the work that we're doing here, I know that there's some other research work that has gone on. Tell me a little bit about kind of what's going on across the state. When we're talking about Kentucky, and is it just UK that's kind of out kind of alone on this, or do we have some other partnerships?
Well, so UK has the only aerospace engineering degree. So for engineering, aerospace engineering, that's pretty much it. But there is a lot of research going on space-related topics in the state. And we talked about NASA Kentucky earlier. So this is a statewide funding mechanism and funds space research. At Louisville, there's a lot going on there. Western Kentucky, and of course, Morehead State has a fantastic program for space system. So CubeSats, and also tracking with their antenna tracking space object. So there's a lot going on through university, but there's also private companies that are in this field as well. So the first that comes to mind is, of course, Space Tango, which is UK grads that started that company that is now flying a lot of experiment. They had one on Artemis. They were one of the last payload to be added to Artemis II, actually. So a lot of our graduate students end up there. There's also a lot of aerospace company in the state. It is the number one export of the state is aerospace. So we have big companies like Lockheed or Raytheon that have a big presence in the state, and that, again, they're hiring our graduates. So there is a potential for our students to go out there, but there's also potential for our students to even stay in Kentucky if they wish us to do so.
If a student is listening to this, or someone is listening who has a student of their own or in their family, and that student is thinking, that's what I want to do, what would you tell them to do? For like a high school student, for example, who's thinking, I want to, this is what I want to do with my college career, what would you tell them to do first?
Get good grades.
Focus on math and science, and then we'll take care of the rest when they get here.
Fantastic. Well, gentlemen, thank you so much for the time. I really appreciate it, and we will definitely keep in the loop on your work and what's going on with this. When is the next? What's the timeline that we're looking at for the next Artemis mission?
I think it's late 27, but I'll step back and give a shout out to the CRUPS and the CREP project. As we had mentioned, we have the only hypersonic flight program at any university in the world, but also like these low-cost capsules in partnership with NASA. They're coming back in November.
October,
November. There are 12 capsules, and there are at least 6 different heat shields that are new that will be flight qualified on our platform for NASA as well, right? So that's going to be the next big event for us before even Artemis III.
Excellent. All right. Well, thank you all so very much. I greatly appreciate it.
Thank you.
Thank you.
Thanks for listening to Behind the Blue. Behind the Blue is a production of the University of Kentucky. For more stories about how the University of Kentucky is advancing our Commonwealth, visit uknow.uky.edu.